Hi everyone, my name is Greg Ruthig. I'm a biology professor here at North Central College. I study the ecology of infectious diseases, and today I'll be talking about a pandemic that has impacted all of our lives, and that of course is the coronavirus pandemic that has upended about everything in our lives. And so what I'll do today is tell you a little bit about the biology of this virus, and then I'll get into epidemiological models, how they work, and how they impact decisions that we make. And finally, I'll finish up with a model that I created of the coronavirus epidemic here in the United States. And what I'd like to do is tell you about how all of those behavioral changes that you have made, things like washing your hands and covering your faces, how that has impacted the course of this epidemic. So to begin, a little bit of coronavirus biology. First, that name corona or crown virus, and you can see that they're actually a family of viruses that have this sort of crown shape when you look into them under an electron microscope. And so I'll point to those little club-shaped things that are sticking off the edge of each of these little viral particles. Those are little proteins that stick off the surface. They're unique to this family, and so that's where they were given their name. Secondly, the genome of these viruses are very different than our genome. So our genome looks a little something like this molecule to the right, a double-stranded DNA molecule. Coronaviruses are single-stranded RNA molecules. And so what that means functionally is that they tend to have a little bit of a faster mutation rate, much faster than we do, which means they change quite a bit. However, one of the things that we're learning about this virus in real time is as far as single-stranded RNA viruses go, they don't mutate as fast as other ones, such as, say, the HIV virus or even influenza. And that's going to be good news when we try to do things like come up with vaccines for these viruses. So as I mentioned, coronaviruses are a family of viruses. So there's many different types of coronaviruses out there. In fact, probably all of the people who are listening to this have been exposed to a coronavirus at some point in their lives. Around 15% of all common colds are caused by some form of coronavirus. There are some more nasty versions that you may have heard of. One is called MERS, Middle Eastern Respiratory Syndrome. This is a disease associated mostly with the Arabian Peninsula. It's a deadly disease. Around 40% of the people who get infected die from this. That's the bad news. The good news is it does not seem to spread very well from person to person. And so outbreaks of this disease have not traveled very far, which is great. On the flip side, SARS, which was an epidemic that went around the world, but was mostly focused in Southeast Asia in 2002 and 2003, is a close relative of the coronavirus that's impacting us today. There are some notable differences that I'll talk about a little in my talk. It actually was a more virulent pathogen, and so more of the people who got that disease died from it. But the good thing about SARS, the SARS virus that struck the world in 2002 and 2003, was that symptomatic people tended to show their symptoms, which meant it was very easy to identify people who were infected and get them quarantined. The challenge with the coronavirus that's around today is that many people are either asymptomatic or they'll be very infectious even before they start showing signs, which has made it much harder to control. And of course, this has turned into a global pandemic that has impacted far more people than that original SARS epidemic that hit us in 2002 and 2003. So I'm going to talk a lot about epidemiology. I've got a few terms and those sort of jargony sounding terms at the beginning, but you're going to understand what all of these mean in just a little bit. There are lots of kinds of infectious disease epidemiological models. What I'm going to focus on for this talk is a model that works for coronavirus. And so some of the adjectives that go along with that is that it's a micro-parasite model. It's density dependent, which means the more people there are, the faster the disease spreads. And the structure of the model is known as an SIR model. So first, that term, microparasite. Microparasite, as you might think, means small, but also a suite of other characteristics tend to go along with being a microparasite. So the big one is that it multiplies fast in a host. And so when we're categorizing people if they're sick or not sick, it tends to be an all or nothing thing. And so a lot of colds are this way. You either have a cold or you don't have a cold. You tend not to have just a long lasting sort of mild cold. You either have it or you don't. And it also means that those infections are transient or really short term. So you get it, you get sick. In some cases you might die, but most microparasite infections, you'll get over it pretty quickly. You can compare that to a macroparasite model, like a lot of big wormy type infections. And so a big something like a trematode or a nematode infection, those can last weeks, months, and sometimes they're lifetime infections. Microparasite diseases tend to be really, really short term. So the structure of the model that we're going to use is called an SIR model. And what S, I, and R stand for are susceptible, infected, and resistant. Sometimes recovered is also used for that R part. So susceptible hosts are individuals who are out there that can acquire infections. They're susceptible to getting infected. In the case of coronavirus, that's almost all of us. We're probably all likely to get infected if we're exposed with this. That's not always the case. Infected just means, like you would think, that you're harboring that disease agent, in this case a virus. And resistant are individuals that have been exposed to infection and then have some sort of, we're going to assume, long-term immunity, so they won't get infected again. This happens over the course of an epidemic. We also, as humans, will cheat this system a little bit and we'll give people vaccines to allow them to skip that whole infected stage and become resistant hosts. Being infected is more complicated than it might sound, and we need to incorporate that into our models sometimes. And so the simplest thing is being infected means you have the virus in you. And so that's what the I stands for. However, not all infected hosts are always diseased. And that's particularly important for this new coronavirus epidemic that's hitting us right now. We know some percentage. That percentage, it's been hard to gauge how many, but as many as maybe even 40% of people who get exposed, get the virus in them that's replicating inside of them, don't show any sign of infection. And so those people might be infectious, which is the last term I've got there. So they're able to transmit the pathogen, but they're not showing any visible sign of infection. That's great for them. That means that they don't feel sick. And it's very, very difficult for a public health official who's trying to do something about this, because without very good testing, there are going to be many people out in the population spreading this disease without even knowing it. And so we call a host that is infectious but not diseased or asymptomatic a carrier. And so carriers are going to be very, very important in this current epidemic of coronavirus. As I mentioned earlier, they weren't as important in the SARS epidemic, and that is a large reason why we were able to control that outbreak and not this one. So the final term that I showed you before was density dependence. And so what this means in general is that the more hosts there are, the faster the disease will spread. And so you can imagine walking into a crowded room and somebody sneezes, the more people in that room, the faster that disease is going to spread. This is opposed to frequency-dependent diseases, which are things like sexually transmitted diseases or vector spread diseases. And what really matters there is what proportion of the population is infected. For coronaviruses, they're almost certainly going to be density-dependent diseases, and so more people equals faster transmission. So I'm going to get into some model parameters for this sort of setup for an SIR model. And the first and probably most important is transmission. And this is usually shown by the symbol beta that I've got right here. Here's the symbol beta. And as important as transmission is, obviously, it's one of the hardest to measure. And just to give you an example of this guy sneezing right here, there's a lot of things that go into whether or not this person here will transmit it to another person. For example, what's the chance that there's a viral particle in one of these droplets? There are a lot of droplets there, so it's probably pretty high. But what's the chance that this droplet might land on a surface that's going to be touched by another person or is going to end up in the nasal cavity or mouth of another person? Well, we don't really know that probability. And then even if it does land on another person, what's the chance that that other person will get sick? These are all very important things, but they're very difficult things to measure. And so what you'll see is, in many cases, epidemiologists will try to measure everything else about the outbreak and then do a little bit of algebra or a little bit of math to be able to figure out what transmission is, because it's kind of hard to directly measure. So in density-dependent epidemics, where the disease spreads faster, where there are more hosts. The most important term that we're going to see is beta, so that's that transmission parameter. It's per capita, so per the number of people you have, times the number of infected, so there's I right there, times the number of susceptibles. So beta times I times S is a really, really important term because that determines how fast new people acquire infections. Okay, so a high transmission parameter, so if something is a really spreadable disease, that's important, but what's also important is the number of infected people and the number of susceptible people that are out there in a population. Another important term in epidemiology is the recovery rate, and that's usually shown by the symbol gamma, sometimes other symbols, but for the most part it's gamma. And so the recovery rate is at what rate does a person start to get better from the disease. This one is a lot easier to calculate, and what you do to calculate gamma is you just do 1 divided by this rate. And so in order to figure that out, say for coronavirus, we know that people are sick for about 2 weeks. This varies a little bit from person to person, but on average it's around 2 weeks. And so in order to figure out what the recovery rate is, we do 1 over 2 weeks, or 0.5 per week. And this is the estimate that I'm going to use in my model a little bit later on. Finally, the saddest parameter that I'll teach you today is disease-induced mortality. And this is usually shown by the symbol alpha. And so this is the mortality rate that is caused by being infected. And so for some pathogens, this can be very, very high. Something, say, like the Ebola virus, if it's untreated, is somewhere around 90% of the people will die within a week or so from that pathogen. This is opposed to the natural death rate, which is usually shown by the symbol D, which is sort of background mortality. And so this is the death rate of everything else except that infectious disease. So this could be from other infectious diseases, from cancer, from car accidents, whatever it might be. This is the death rate of that population for everything without the infectious disease. But the one I'll focus most on is, because we're worried about infectious disease, is disease-induced mortality. So here's the model. Here's the SAR model. If you are a visual person, you're going to like this figure here. And if you're a mathematics type person, you're going to like the next slide even more. So this is sort of how we think of SAR models and boxes. So we have a population of people being born. So there are births. When people are born, we assume that they're susceptible, and that's a pretty good assumption. There are some diseases that you can acquire from your mother, but in this case, we're going to assume that doesn't happen. So you're susceptible. If you get infected at some point, you move into the infected class. And then if you're infected, hopefully you will recover from that disease. And so you move from the S to the I to the R class if you get infected by this pathogen. Here's a sort of flow chart of how that works. Again, all of the classes, infected, recovered, and susceptibles, have babies, so they're born. If you're a susceptible person, 2 things can happen to you. You can die from natural causes, or you can get infected, and that's determined by the transmission parameter beta there. If you're infected, there are 2 things that can happen to you, actually 3 things. You can die for 2 reasons. You can die from natural causes, D, or you can get infected. So there's a die from an infection, and so there's alpha. Again, that's going to vary a lot from disease to disease. A normal cold, that's going to be really low, but we're learning right now at least some percentage of the people who get this novel coronavirus will die from that disease. And hopefully, though, if you get infected, you will recover. And again, that's determined by this recovery rate gamma. Recovered people, the only thing that can happen to them is die from natural causes, hopefully at a ripe old age. Here's what the equations look like that go along with this model. And so these are rate of change equations. And so this is the rate of new susceptibles you get over time. How does that change? Well, we can see here that we add new susceptibles by being born. So this is a birth rate, and we multiply that birth rate times all the members of the population, the susceptible, the infected, and the recovered people. There are some models that reduce it for infected people. They might not have as many babies, but in this case, we're going to assume that they do. Then you can lose susceptible people by natural deaths, and so whether or not they got sick from other reasons or got in a car accident or wherever it might be. or you can lose susceptible people by getting infected. And so here's that beta SI term that I told you about earlier. So this is a really, really important term in this model. So this is negative, and so you lose those people, and this is our rate of new infection. So it's determined by transmission times the number of susceptibles times the number of infected people in the population. That same term that's negative here in susceptibles is positive down here. So this is the rate of change of new infected people. So it's beta times S times I, and then you lose infected people by them dying, either from natural causes or from the disease, or hopefully they recover. And so here's our recovered class here. So we gain recovered people by those people who recovered from getting infected, and you lose them because they die from natural causes. So that's our model. Here's what it looks like on a graph. And so I want you to focus on the graph on the left right here first. And so this is what those three classes look like over the course of infection. So first of all, I'll start with susceptibles. In the beginning of an epidemic, almost always everybody starts off as susceptible. That's certainly probably what happened here in the United States. We were all susceptible to the coronavirus. But as we got infected, that number goes down. And so we get people start to get infected. That's red line here. And then we tend to get this sort of hump-shaped distribution. And that's because people start to recover. And so they become resistant to the disease. And so when we're multiplying beta times S times I, we start running out of the S's. Not as many people are susceptible anymore. And so that epidemic will run its course. This model, you may not think it's simple, but this is considered a fairly simple model, actually explains natural or epidemics that have happened in the real world pretty darn well. And so an example I'll show you right here, this is an influenza outbreak at a British boarding school in 1978. The model here is shown by this black line going up and down, looks really very similar to the cartoon model I showed you to the left. And those black dots are the actual number of infected boys at that school. And you can see the model and the data line up pretty well. And so these models are used by epidemiologists a lot because they're pretty effective. One of the most important terms that come out of these models is something that you may have seen in the news by now, and that's the basic reproductive number, often shown by the symbol R naught. And so I want to go show you a little bit about how R naught works. So what R naught says in sort of plain English is this is the number of new infections caused by a single infected host. And so you can imagine a new person shows up on an airplane into the United States who's carrying the coronavirus. On average, how many new infected people are they going to infect? In this example here, R naught is 5. And so one person infects 5 new people, again, on average. So the magic number that I teach all of my students in my infectious disease classes for R naught is 1. Public health officials, really, it's very hard for them to reduce transmission down to 0 and get R naught down to 0. But what they can do is try to get R naught less than 1. Because if you can get R naught less than 1, what that means is that this epidemic will eventually fade out. It'll go away. And so R naught of 1 is really the magic number. We're really trying to get this number less than 1. And then at that point, the epidemic will fade out on its own. So when R naught is 1, it just sort of replaces itself. Each person infects about one other person. But when it's less than 1, the epidemic goes away. And of course, if it's greater than 1, we're going to see some sort of an outbreak, which is what we're facing right now. There are many ways to calculate R naught. I'm going to show you how to do it in the models that I just presented to you. And here it is. And as I go through this, I want you to think about how you might be able to change these parameters if you were a public health official. So here's R naught on the left, and you can see it's calculated by a fraction. And so remember, as things get bigger at the top of the fraction, R naught will get bigger. As things get bigger in the bottom of the fraction, that will make R naught get smaller. So what make R naught get bigger? Well, beta, that seems kind of obvious. And so the faster this pathogen is transmitted, the higher R naught is going to be. The second thing is the number of susceptibles. And so if coronavirus invades a population with lots of people, it's going to spread to more people than if it infected a population with fewer people. Again, that seems kind of obvious. On the bottom, you can see that there's the disease-induced mortality. That's how virulent the disease is. And so I'll give you an example of how a high alpha actually keeps R naught small. When the first Ebola outbreaks in 1976 and a few times in the 80s and 90s, Ebola had an alpha of around 90%. 90% of the people died, and most of the time that was before they could pass it on. And so even though that's awful to have a high alpha rate for the person who's infected, it's actually good for the course of the epidemic because it makes R naught smaller and makes the disease fade away faster. Another thing that makes the disease fade away faster is that people just die from natural causes more quickly, and so they're not going to spread the disease. And then finally, the recovery rate. So a high recovery rate, if somebody gets better really, really quickly, they're not going to be able to spread it to a lot of people. And so a question I often have in my infectious disease classes, I'll show students this model and I'll say, imagine you're the public health official. What sorts of things can you change in order to get this disease to go away and hopefully get R naught less than 1? One of the most obvious ones is, can you impact transmission? Okay, and so doing things like washing your hands or wearing a mask reduces transmission and it's going to lower R naught. So that's great. How could you reduce the number of susceptibles? The big tool that we have to do that are vaccines. Okay, and so what vaccines do is turn somebody from a susceptible into a resistant. And so we can reduce the number of susceptibles through vaccines. Unfortunately, we don't have one for the novel coronavirus, but hopefully we will at some point. Down at the bottom, there's not as much that you can do. I've had some very unethical students answer my question by saying, well, you could kill more people. That's obviously not something that we could ever do in a human population, but it is something that is done by farmers. And so if there's an outbreak of a disease, say of hoof and mouth disease or mad cow disease, farmers have culled or deliberately killed their animals in order to get that outbreak to go away. But finally, by impacting gamma, by giving somebody medicine, you might be able to allow them to recover faster. Again, unfortunately, we don't have great medicines that have reduced this. We have a few that are promising at this point, but certainly no cure-all for coronavirus. But in the example, say, of HIV, there are now antiviral medicines that do two really great things. Number one, they allow that person to live a long, healthy life. So that's great for the personal health side of things. But on the public health side of things, it allows that person to do is to get a viral titer, so such a low amount of virus in their body that they're unlikely to spread the disease. And so this is a case of increasing recovery, slowing down the course of a pandemic. Here are some examples. The numbers are kind of small of some R naughts of other diseases that are around that I just wanted to show you. And on the top of this list, you can see measles. And so measles in some cases had an R naught as high as 16 or 17. And what drives that is measles is an incredibly contagious disease. Transmission levels are very, very high, such that a single person walking into, say, a classroom could infect the bulk of the rest of the class. So a very, very infectious disease. But that ranges, again, you can see anywhere from 2 to 17 or 18, depending on each of these diseases. The good news is all of the things on the top of this list, we now have vaccines for. So even though they're highly transmissible diseases, we've been able to reduce R naught for these diseases by changing the number of susceptibles. The only one on there for which we don't have a vaccine, of course, is HIV down there at the bottom. And so we've had to rely on changing recovery by giving people medicine or through public health measures to reduce transmission. So what does R naught do to the course of an infection? I'm going to show you, I'm going to answer this question through the use of a graph. This is a graph. This is a figure that you may have seen on your social media feed by now. This is the famous flattening the curve graph. And so what you can see on this graph is I've got time on this axis. And so this is a computer model, but you can think of this over the course of a coronavirus epidemic. And here's the number of infected hosts. So the black line here is the number of infected hosts when you have an R naught of 6. And so you can notice a couple things there. Number one, the peak is very high. So that was one of the big reasons why people advocated for flattening the curve, is because when the peak of infections gets very high, you can overwhelm a healthcare system. So that's important. One of the other things that you might see that may be a little bit of a positive is that outbreak occurs very, very quickly, and then it fades out more quickly. So if we compare that to our R naught of 1.5, this epidemic does take a longer period of time. However, if you look at the total number of infections caused by this outbreak versus the outbreak with an R naught of 6, more people get infected. In the case of coronavirus, more people die when you have a higher R naught. So there are lots of good reasons to have a lower R naught. The only real advantage of a high R naught is the epidemic happens faster, but that isn't always a good thing. So what I'll do for the rest of the talk is use that model that I just taught you and show you how it applies to the epidemic here in the United States. I chose the United States rather than the whole world because we have pretty good data here. And so we've been able to follow this epidemic from beginning to the current date. We've got oceans on several sides of us, so there's not a lot of immigration and emigration going on in the population right now. And so this was a nice contained unit, but I also thought it would be relevant to a lot of the people who are listening to this. Hopefully a lot of the things that I will show you here in the epidemic here in the United States will apply to anywhere else in the world. So first, some parameters. I will not spend a lot of time on these numbers. Please don't try to remember them. But these are numbers that I got from the CDC, where I estimated the number of babies born per week, the number of people who would naturally die per week in the United States. I rounded a little bit to get a population estimate of 328 million people. It was difficult to know how many people came into the United States infected. I estimated 100. It turns out when I made that number bigger or smaller, it didn't really matter over the course of the infection whether it was 100 or 10 people or 1,000 people who came in. The epidemic looked pretty similar once it got going. And then finally, one of the numbers that I've changed quite a bit several times is disease-induced mortality. This has been a number that has been all over the board, and you'll see that in news stories. But what I estimated is that 0.5% of people die within 2 weeks who get it. This is obviously very dependent on several risk factors, and particularly age, but this seems to be a pretty good estimate. I thought it was low at first, but it seems to be a pretty good estimate of the percentage of people who will die each week due to coronavirus. So one of my challenges, one of the things you'll see that was not on those parameters was I did not know what the transmission rate of this disease was. As I mentioned in the beginning of the talk, transmission rate or beta is a very, very hard thing to measure directly. And so what I did was I took a look at the number of coronavirus deaths. I thought that that was a pretty reliable metric. If somebody died and were tested for coronavirus, we knew that was a coronavirus-caused death, as opposed to infection rate, where assuredly we're missing lots and lots of people who get infected and we never even know about it. And so I used coronavirus deaths as sort of my guide, and then I manipulated transmission levels in order to get my model to fit the data based on the number of deaths we saw. So based on all of that, and you'll see how this works in just a minute, I came up with this transmission parameter, beta, of 6.865 times 10 to the negative 9. That is a really tiny number, but having seen transmission parameters in other epidemics, this actually isn't that amazingly small. I know it's a number so small to get your head wrapped around, but in a second I'll show you how that number works and how that explains the outbreak that we've seen so far. So I'm going to be showing you a lot of graphs that look a lot like this. And so you can see here is on the x-axis are our dates. And so there's early March in a more innocent time when we weren't quite as worried about coronavirus as we are today. And then I'm going to end up right near the current time that I'll go into the school year on some of the later graphs. This is the number of people, and so we'll be looking at the number of people who die, the number of people who get infected, and the number of people who recover in a lot of these different graphs. And so what I've got on this graph here is the actual number. So this yellow line shows the number. These are the data from the famous Johns Hopkins website that have been keeping us all abreast of how many people are getting infected and dying over time. The data aren't perfect. They've been a little messy, but they've been pretty good. On the blue line here is my model. And so this is what my model says the course of the infection ought to look like. And so what you can see is with that estimate of the 6.865 times 10 to the negative 9th transmission parameter, my model fit the data really, really well until this point, until we hit somewhere in the middle of April and the two models diverge. My model says lots of people should have died, and thankfully far fewer died than my model predicted. So think back, I know it was a long time ago, seems like a lifetime ago. Think back to what changed in your life in late April, late March that might have caused these two things to diverge. Well, just about everything in our lives changed, didn't they? We closed schools. We closed North Central College. My kids got sent home from school. It was a very dramatic week there towards the end of March. We started washing our hands so much that it felt like our skin was going to fall off. We were paranoid about anything that we ever touched. We moved from having online to having online meetings. So I've got a picture of a Zoom meeting right there, something that we've all gotten used to in a very short amount of time. And then finally, it took us a long time to get there, but we finally started wearing masks. And we now know that masks in particular are very effective at reducing transmission from an infected person. And so a regular cloth mask that you might have at home does an okay job of protecting you from a viral particle that might be floating on the air. It does an excellent job of preventing an infected person from spreading that to other people. And so again, it took us a while to figure this one out, but now hopefully this is part of your daily lives. Anytime you're going out in public, you ought to be wearing one of these masks. So what did all of these changes in behavior do to the epidemic of coronavirus? Well, what I did is I reduced the transmission parameter on several dates in order to get the model to fit the data. I reduced it on March 29th, on April 5th, and on April 12th. And you can see when I did that, the yellow line and the blue line. So my model and the actual data fit very, very well. Okay, so my model's explaining it with a reduced transmission parameter. So how well did we do, and how can we use the model to estimate that? And so what I did is I compared that initial level, that 6.685 times 10 to the negative 9th, which is what we had in February, to the transmission levels that we have today. And the answer is we're around 17% of that original transmission parameter. That's something we ought to be very proud of. During that time, we came up with a few medicines that helped a little, but really no medicine that cured a lot of people. We did not come up with a vaccine. All we did was change our behavior. But by changing our behavior, by doing all of those annoying things that I just described in an earlier slide, we were able to reduce the transmission levels to 17% of their original levels here in the United States. So what does that model look like in terms of infected and recovered hosts? And so you can see on this model, I had to change the axes a little bit. And so before I was showing you axes in the thousands, now I've got 10, 20, and 30 million people. You can see my number of deaths are so low that you can't really see them showing up. They just look like they're hugging the bottom there. But here's the red line with the number of infected people. And one of the things that struck me initially about when I first saw this was look how many people were infected in early April. Almost 10 million people, so a large number of people. If you've been following the data in the news, you know that we've had only about 2.5 million documented cases, but we surely have been missing lots of people. On the gray line here, you can see the number of recovered hosts, and so these are people who got infected and then recovered from the disease. Recent estimates from the CDC that looked at data from things like blood bank, they looked at antibodies, so people who we know have been exposed to the disease but then have recovered, suggest that right about now, so here we are in late June, somewhere around 20 million people in the United States have been exposed to coronavirus, and my model actually predicts that pretty well. I thought when I first saw that this was very, very high, but it turns out it's probably a pretty good estimate of the number of recovered people. And so again, even though we've only had 2.5 million people with documented infections, that number is certainly much higher. The other bit of good news that you'll see from this is you can see a curve that was swooping up that should have gone up probably into the tens and maybe even hundreds of millions of people. That stopped because we changed our behavior. And so we changed the shape of this curve. We flattened the curve. We did it, guys. Good job. And so now we're on a downward course. So I know that many of you are probably anxious to get back to your regular lives. We see this in the news all of the time. People are anxious to go out, to see people, to go to concerts, to go to sporting events, and to get the economy going. And so I played with the models a little bit to say, well, what if we did let up on the reins a little bit and say went back to 50% of February levels of transmission. So 50% of the levels when we weren't doing anything to slow down the spread of the disease. But still, doing things like washing hands and being careful about the disease. So what would happen if we returned to 50% levels? And unfortunately, the answer is a bit sobering. So again, here are the two lines. Here's the recovered line, and here's the infected line. I changed the transmission parameter to 50% of levels, and here it's 17%. And then here in the beginning of July, I changed it to 50% levels. And what you can see is we'll have a second wave that's far bigger than our first wave. This is what we already lived through in April and May. This is what we'd be facing at the beginning of the school year. And so what this tells us is that we are going to need to be able to keep very low transmission levels in order to avoid a second wave of the coronavirus here in the United States. The next question I said is, well, what level can we live with? And so I played with transmission parameters over and over and over again, and I moved them around a little bit. And I said, well, what levels of transmission will keep us from having a big second peak like the one we saw on the last slide? And the answer was around 25%. If I kept transmission levels at 25% of their original levels back in early March and February, we avoided having that big second peak. 25% is not much bigger than 17%, which is what we've been currently living with. And so that means we're going to need to still be very, very careful about how we behave in order to keep and avoid a second wave of coronavirus. Another term you may have heard in the news a lot recently is this idea of herd immunity. Herd immunity comes from farm animals, and it's an idea where if you have enough resistant people, enough people who've been exposed to the pathogen and then recovered, that the disease will fail to spread. Basically, what you do is you reduce the number of susceptibles. It turns out you can calculate herd immunity using R naught. I've got the equation down there that I won't go through, but this is it's not too hard. And basically, the higher the R naught is, the higher the percentage of the population that you will need to get infected. Normally, this equation is used by public health officials to determine what percentage of the people of the population would need to be vaccinated. In the case of coronavirus, we don't have a vaccine, but there are people who have advocated for allowing the epidemic to run its course, basically, and infect all the people that it's going to infect in order to reach herd immunity. The nation of Sweden is the most notable case where that's actually sort of been their public health strategy. And so I asked the question based on the parameters that I determined for the coronavirus epidemic in the United States, what percentage of the population would need to get infected in order to reach herd immunity? And the answer was 77%. To give you some perspective on that number, we are currently less than 10% of the population has been infected at this point. So that would mean that 7 or 8 times the number of people who have been infected now would need to get infected. Another thing to think about is that at this time, we've lost about 126,000 people who have died from this disease. So we would likely need to multiply that number by 8 as well. So we'd be pushing around 1 million people would need to die in order to reach herd immunity in the United States. I think most ethical people would find that number unacceptably high in order to be able to go back to our normal lives. And so, again, this epidemiological model really helps gives us a sense of why, in my opinion, this is a very bad strategy. So what can we do at this point? I know we've been living a turned upside down life for quite a period of time, but right now we don't have a vaccine to reduce the number of susceptibles. The big thing that we can impact is transmission, and this is what we've been doing for the past few months. And so I'm going to give you some of the advice that I'm sure have been given lots and lots of times before. Number 1, continue to wash your hands and exposed surfaces. Although we're learning more and more that the bulk of new infections are probably coming through the air, coronaviruses can survive on surfaces for up to a couple days. And so it is worth your time washing your hands and surfaces that may have been touched by other people. So that's worth your while. But probably more importantly is going to be to continue wearing those masks. As I said earlier, wearing a mask is particularly important for a person who is infectious at that time. And as we know with this novel coronavirus, many people who are infectious don't know it. And so even if you feel fine, it's worth wearing a mask because you're doing a favor for all the people around you. Other bits of advice, we're learning more and more that the virus can increase in density if it's indoors, and so you want to avoid spending too much time indoors with lots of people. The more you can spend time with people outdoors, the better. And I'm going to throw in there that this doesn't just mean strangers. Your friends and family, as much as you love them, are just as likely to be carrying this virus as anybody else. And so if you really are dying to see your friends and your loved ones, the best thing you can do is have a picnic, do something outside to spend time with them. And finally, this is something that, in my opinion, we're behind schedule on, is contact tracing and quarantining. Identifying people who are infected through effective testing, but also identifying people that they may have come into contact with, and so those people can get quarantined as well. So get them out of the public circulation, allow them to spend some time at home, watch some Netflix, and stay out of the general population so they're not continuing to spread the pathogen around. So to conclude, I've given you maybe some sobering statistic. We've been working hard in order to keep this disease down. We've done a good job. We should pat ourselves on the back. We've reduced transmission to around 17% of original levels, but our job is not done yet. We're going to need to continue to work very hard in order to keep transmission low for a long period of time so that we can at some point go out and do all those things that we've been dying to do. On the flip side, I hope that this information is somewhat empowering to you. Until we have a vaccine, and we have some very smart people working on vaccines and medicines that will reduce the impact of this epidemic, really the power is in our hands in order to reduce the course of the epidemic. And I've shown you with these models that we've already done that. We've already had a big impact on the course of the epidemic. And so we have the power to continue to do so. And so I hope you keep it up as hard as it is. Thanks so much for listening to this talk. If you have any questions, I'm happy to answer them.